Hi, in this video, we're going to learn how to calculate the effective annual rate. So imagine you have amount of money you want to save in a bank, and you'll be quoted at a bank, say a percentage for your annual percentage rate. Okay, we also call it the quoted rate, and you don't necessarily receive your payments annually. Okay, so if you receive your payments semi-annually, quarterly, then the effective annual rate is going to be different from your annual percentage rate. Okay, so let's use this as an example. For example, if you have £100 you would like to save in a bank, and you'll be quoted an annual percentage rate or APR at 10%, okay, and you receive your interest annually, then how much is your £100 going to worth in 1 year's time, or what is the future value of your £100 if it's compounded annually at 10%? So it's simply 100 times 1.1, which is 110. Okay, so if you receive your interest payment here, then your future value of your savings is going to be £110. So what if you receive your interest in 6 months' time? Okay, so it's compounded semi-annually. You don't receive 10% of your 100 here because you receive twice. So this interest payment will only be a half of your 10%. So it's going to be 100 times 1.05 in 6 months' time. But in another 6 months, which is going to be the end of year 1, you're going to compound it once more. So the future value of your £100 is going to be 110.25. Okay, and similarly, if it's paid quarterly, then you receive your first payments in 3 months' time, and you have a third payment in 9 months' time. Yeah. So what is the future value if your saving is compounded quarterly? Then it's going to be 100 times 1.025 to the power of 4, and it's going to be 100.38. Okay. So as you can see, the more frequent the compounding period, the higher the future value. Okay, so we can generalize this by using another example here. Okay, so let's say our APR in this case is 6%. Okay, because 6% is something easier we can work with. Okay, and the compounding periods, or the compounding intervals, will be, let's say, start with 2. Okay. So, which means we'll be paid semi-annually. Okay, so twice a year. Okay, and how do we calculate the effective annual rate? Okay, so effective annual rate is not 1.1. It's not 6% anymore. So it's going to be 1 plus 6% divided by 2 to the power of 2 and minus 1. Okay, this is because you will receive your first payment not at the end of the year, but at the middle of the year. So you compound it twice, but your payment is also halved, right? So this should give you 6.09%. Okay, so what if we compound quarterly, which means our compounding intervals will be 4. So 1 plus 6% over 4 to the power of 4 minus 1, and that gives you 6.136%. Okay, right, and we can increase this, let's say, to monthly. Okay, and so we compound it even more frequently. Okay, so this is similar to a mortgage because you pay monthly, right? So it's going to be 1 plus 6% divided by 12 to the power of 12 and minus 1 here. So it should give you 6.168%. Okay, so let's go to the extreme. So what is the shortest intervals that you can think of? So is it like daily, or by any second, or tiny bits of seconds? So if it's so short, the compounding intervals, they're so short that they're continuous. That's the extreme here. So basically, if we're continuously compounding, then we have intervals that approaches infinity. The number of intervals will approach infinity here. Okay, so the problem is, let's say 6% divided by some n here, which is your intervals, the number of your intervals to the power of n minus 1. What's this going to be? right? As n approaches infinity here. Okay, so we can generalize this and try to prove this one by not just using 6%. We can use any percent, okay, any percentage. Let's say R here, okay? Let's say R, or just write R instead, okay? So what if we have R here as our APR, our annual percentage rate, and we are continuously compounding? How do we calculate the effective annual rate? Okay, so we're basically trying to answer the question of what is the number of R over n plus 1 and to the power of n. Okay, how do we calculate this? With limit n approaches infinity. Okay, so this is one of the most famous mathematical equation or expression, and we're trying to prove it that it converges to a single number rather than just diverging. Okay, so how do we prove this? You can think of this as a certain number here. Okay, so y is this thing. Okay, so we don't like the exponential numbers here, so we take the logarithm on both sides, which gives you n log 1 plus r over n. Okay, so we can ignore this bit for a second. Okay, so how do we do this? We can simplify it by giving it a denominator of 1 over n. Okay, so they're the same, right? So now we have our numerator. If n is approaching infinity, then this goes to log 1, which is 0. And this goes to 0 as well. So we have the 0 over 0 form, which allows us to use the L'Hopital principle. Okay, so we're basically taking the derivative with respect to n on your numerator and on your denominator simultaneously. So what do we get? So we'll get here. So on the denominator, it's going to be minus 1 over n squared. Okay, and on the numerator, we first have 1 over r over n and 1 plus r over n. Okay, and multiplied by r over n squared. Okay, right. As n approaches infinity here, okay, we can first cancel out these two numbers, right? These two numbers, the minus 1 over n squared can be canceled out. So we're left with r over 1 plus r over n, okay? And if n is sufficiently large or approaches infinity, then we're simply getting r here, okay? So which means this part here, okay, this part here is going to be r. So y here, or our original expression, is going to be e to the power of r. Okay, so now we know if with a continuous compounding, the effective annual rate is simply e to the power of r and then minus 1. Okay, so there is an upper limit to which how high this interest rate or this effective annual rate can go. It doesn't increase to infinity. It converges to a single number, which is this one. Okay, so in the following videos, we will try to solve relevant problems based on calculations of effective annual rate. I'll see you there.